want to point out, so today we're going to kind of talk big picture, a little bit of technical theory kind of stuff, and then starting on Monday, we're going to get our hands dirty with the circuit boards. But there's some stuff we need to do in advance of that. So a lot of this, all of the notes and things that I've written, I keep them on Dropbox, which means when I update them, if you re-click on this link, it's going to take you to the most recent version. Same thing with the notes or what I'm going to write on my iPad. Think of it like I'm using that instead of the chalkboard. And same thing, I synchronize it to Dropbox, so when you click on it, it's the most recent version. And I'll add that link because I just started the new document, so that part I still need to do some setup for. But anyway, so what we're going to start talking about are transistors and logic gates, and we'll spend a week-ish or so on this stuff. And these notes are kind of been undergoing significant revision for years and years and years, as I've been, coming up with new ways to do things. But anyway, so that's kind of some of the stuff we'll talk about in here today, and other things are things that aren't in here, but I want to add to it, and it's just, a matter of getting to it. So, so just wanted to point that out, that we'll use some of this today, but not all of it. And then we'll continue, obviously, with that next week. Okay, I think before we do that, let's go back to and actually use the bastion of all knowledge of Western civilization. Okay, so a computer fundamentally needs to have some sort of ability to, well, okay, let me back up. An electrical computer needs to have some sort of ability to switch whether or not certain circuits are on or not. Okay, and the switch part is the key. There are different things you can use to control switching, and basically 3 different devices have been used historically to do this. Okay, so how many of you guys started watching the documentary series? Yeah? All right, so have you gotten to the parts about Konrad Zuse or not yet? Not yet? Okay. So Konrad Zuse, German, and you can almost think of him as sort of like the computer equivalent of Werner von Braun. So similar time period in Germany, and he basically was using telephone relays as his switching devices. Now, those are electromechanical, meaning that they involve electricity, but there's also a moving part. I mean, it's kind of like you can almost think of a telephone relay as being a really, really fancy wall switch that you could control electrically whether or not it turns on or off. Okay, but a wall switch, right, is an electromechanical device because when you flip the switch, what are you doing? Yeah, well, you're turning it on or off, but there's a moving part there, right? So that's the mechanical part. Okay, so Zuse used telephone relays, and because partly that's what he was able to get a hold of in Germany. And here's maybe some pictures of a bunch of them. One of the things that I want to do now that I think about it, I was thinking about this on the drive in this morning. A lot of these relays are modern solid state relays, but I need to get going on eBay and like buy up like a dozen actual telephone relays that would have been about the time period that Zuse was working, just so that I can be like, hey, here it is, right? Okay, so he used telephone relays. They're electromechanical. The mechanical part means that they're relatively slow in terms of the speed it takes or the time it takes to switch from on to off, or vice versa. Okay, on this side of the pond, if you will, another device that you could use is a vacuum tube. Okay, and here's a picture of a whole bunch of these things. Okay, they came in lots of different varieties and sizes and whatnot, and they were originally used as amplifiers. Okay, so this was sort of a repurposing of a device um, that was already used in other contexts. Okay, so how these were used as amplifiers. So if we think back to say, well, the 1920s or 30s, right? What kind of technology or what kind of devices would people of means had in their homes? Yeah, radios. What else? Starting to, yeah, that and they were, but they were not nearly as advanced as our washing machines. Maybe early kind of refrigeration devices or ice boxes, okay, but not a whole lot of convenience technologies, right? They possibly also would have had some sort of telephones at that point. And maybe also, I mean, if they're going to have radios, they also need to have electricity. And so they probably have indoor electric lighting, um, possibly some sort of like fans and things like that for air handling. Um, and the radios, they might have had hot water and nice plumbing and whatnot. Um, people of means, shall we say, were not having to be going out to the outhouse in the 20s, although plenty of people did at that point. Um, so, yeah, but they would have had radios. Okay, probably most families only had one of them, and it would have been in the living room, much like TVs were. Uh, like when I remember when I was growing up, the TV that we actually watched TV on, we only had one of them because it was relatively large, um, and it was in the living room, right? And it wasn't until maybe a little bit later that I had like this tiny little TV that I could play my Nintendo on in my own room. But nowadays, how many TVs do you have in your houses? Lots, maybe even more than the number of people that live in that house. Okay. But yeah, with the radio, right, what you need is an amplifier because the signal, the radio signal that's being transmitted to you, comes in and it's a very weak signal electrically. You can't just plug speakers or plug headphones in or something into a radio, capture the signal and expect to actually hear it. It's way too faint for human ears. Okay, so what you need to do is to amplify that signal, and vacuum tubes are a way of doing it. Um, and I'll kind of draw sort of a schematic of the idea of how these things work in a minute. Um, okay, but I mean, you look at them and they kind of look like light bulbs, right? Um, and when I say light bulbs, I mean like incandescent light bulbs, which you guys are, you know, starting to get young enough that you may not really have used a lot of incandescent light bulbs in your lifetime, because you guys were all born, what, after the year 2000, right? Or was anybody born in the year 2000? Do I have any 90s kids? No? Okay, so, my old timers here, born in the year 2000, when I was in freaking high school. Get off my lawn. Okay. We had to walk uphill both ways in the snow, by the way, and fight off rabid pterodactyls. So, yeah, okay. So, yeah, but if you were born in the 2000s, you probably don't really remember much before about, say, 2005, 2006, right? When you guys would have been 5 or 6 years old. Okay, so do you remember changing light bulbs or having to change light bulbs when you were younger? Not very often, okay? And one of the reasons is in about '04, '05, or somewhere in there, the compact fluorescent bulbs started to become more common, and uh, they were still more expensive than incandescents, but they lasted a lot longer. Um, and by 2010 or so, they were almost as cheap as regular light bulbs. And of course, nowadays, if you go buy light bulbs at, if we drive to Home Depot, and we go to the light bulb aisle, what are mostly we going to see? Yeah, they're all LED bulbs, right? And they're going to last like, it's sort of the irony of an LED bulb. The bulb will last longer than the thing you're plugging it into, probably, right? And so the incandescent bulbs, though, You can still buy them because they still do have some uses. Does anybody work in Sparks or any other kind of food service? No? They're used still for heat lamps, right? You know, when you want to keep things warm on a food line or something. Or does anybody have a lava lamp? This is kind of dating, right? You still want to use an incandescent bulb in the lava lamp, not because you need much light out of it, but you do need the heat because that's what makes the lava do all the, the thing. Um, and Anton, I bet you're, you know, getting monumentally baked too with your lava lamp and yeah, listening to Jefferson Airplane or something and no. Um, yeah. So, but point being, the incandescent bulbs, right? They do put out light, but what do they also put out a lot of? Heat, right? And that's annoying if all you want is the light. Okay. They also burn out pretty frequently. And vacuum tubes are much like that in the sense that, well, they're not really putting out much visible light. They're not designed to do that. But they do use a lot of energy and therefore are going to have to dissipate a whole lot of heat. Okay. And because of that heat, they also burn out like incandescent bulbs relatively frequently. Okay. Now, a radio might only have like one or two of these things in it. It's not like you needed a bunch of them. And so, if your vacuum tube burned out in your radio, or then later your TV, well, what would you do? You'd buy a new one. Okay. And obviously, I mean, even I'm way too young for this, but I was talking with my dad about this, and they had the same thing when he was a kid, and of course, he was born in 1955, so they did have a television, but the television also had some vacuum tubes in it. And what would you do if the TV or the radio stopped working? Well, you'd suspect that maybe the tube was the problem, but it could be something else, right? So what would you do? You'd pull the tube out and you take it with you to the hardware store or even the drugstore. This is kind of crazy, right? You'd go to like CVS or Walgreens. Well, I don't think CVS existed back then, but you'd go to Walgreens. That certainly existed. And, there'd be one of the aisles that had just racks of different tubes, but they would also have a tube tester that would fit various different ones. And you would plug yours into it, and it would tell you whether or not the tube was bad or good. And if it was good, then you knew that, well, the TV had some other problem. And so you'd take it to a, repair person. And if not, likely the tube was bad. Well, there's the shelf with all the different ones, and you'd find the correct model and go pay for it, and off you went, right? And then throw away your old one. Okay, so these things burned out a lot, and which limited early computing because if you have one or two of these in a radio or a TV or something like that, and one of them burns out, is that the end of the world? No, right? I mean, you replace it, you move on with life, right? Not the end of the world. Okay, and maybe better put, let's say that you have a TV and it has two of these things in it. Okay, what are the odds that both of them are working at any given time? I mean, not you don't have to quantify it numerically, but just sort of roughly, what would you expect? Pretty good, right? Very good odds that at any given time, both of them are working just fine, right? They do burn out, but not all that often, right? I mean, if they're burning out on the period of a month or two, then you can expect on any given day, they're probably both going to work just fine, okay? All right, now what about if you have 1,000 of them? Then what do you think the odds are of all of them working at the same time? Not as good, okay? And the way to quantify this would be, let's say, for example, that on any given day, they have a 99% chance of being working just fine and a 1% chance of being busted, okay? If I have two of them, what's the chances that uh, both of them are working if they have a 1% chance of failure and a 99% chance of success? How would I do this computation? Roughly, okay, but let's actually do the computation, okay? So what's the chance that either one of them is busted? 1%. And the chance that they're both working is 99%, and we need both of them to be working. So what I would do is multiply 0.99 by itself, okay? And we get 98.01, right? So 98 in this case is a pretty reasonable estimate, but that's how I would compute it, okay? 98%, pretty good still, right? But that's just with two of these things. All right, what about if I change this to being 1,000? Pretty low, okay? Now, I am making an assumption here, right, is that the chance that they work is 99%. Maybe it's actually 99.9% or something, okay? But you get the idea here that if you have lots and lots of these things, the probability that everything is working all at once is way lower than if you just have a few of them, okay? Does that make sense? Yeah. Okay, and you know, maybe it's not exactly this number, but you guys get the idea here. Okay, so this really limited early computers that use things like vacuum tubes, because can you have a thing that's got 1,000,000 vacuum tubes? It'll never work, right? Because there's always going to be one of the damn things that's burned out or something. Okay, and also, what's the other problem, if you could imagine? How much heat does, say, one incandescent light bulb put out, or how much power does it use? Yeah, do you guys remember? I mean, we still measure light bulbs in this unit, even though we don't. Yeah, like usually when you buy a light bulb, it's a 60-watt equivalent. Okay, it doesn't actually take 60 watts of power. So why do we still say 60-watt equivalent? Well, what that means is it gives out about the same amount of light as a 60-watt incandescent bulb. And that's just the units. Although nowadays, I think light bulbs also tend to have like the number of lumens stated, which is a better measurement uh, than, you know, measuring things in terms of, you know, how we measured light bulbs in the 70s. And it's kind of like every now and then I see memes like this go across on Facebook or whatever, where it's like, yeah, sinkhole opened in the middle of Main Street that was like 3 washing machines across. And the caption says something like, Americans will do anything to not use the metric system, right? No, how do you feel about that, Mr. Bullock? Yes, okay. But you only half use the metric system, you Brits, right? Because huh? Yes, exactly. You still use miles, but everything else is still metric, except weight. Because don't you still use like stone or whatever? Hmm. Now, what is a stone anyway? 14, yes, because that's totally logical, right? Um, yes, anyway. Um, yeah. So, okay. So these things burn out a lot, right? And they use a lot of energy. Um, and a lot of that energy is sort of wasted as heat. So you could imagine packing 1,000 of these things into a room, like you guys think it's hot down here to begin with, right? Imagine having 1,060-watt light bulbs going on, right? That's, you know, 60 kilowatts worth of heat being dissipated. That's a lot of heat. Okay, so fortunately, a new invention was developed in the, and we'll go to Wikipedia because they've got some good pictures of these things. Okay. Here are what some different kinds of transistors look like. They're very, very, very small, right? Like the size of your fingernail kind of thing. They're also solid state, so they have no moving parts, so that's a benefit compared to, say, the telephone relays. But they also use way, way less energy than a vacuum tube. And it's pretty hard to burn them out. They don't just die after 6 months of use like a vacuum tube does. And in fact, really about the only way that you can burn one of these things out is to be stupid and like put too much electricity through it, or if it's defective from the get-go, in which case you'll pretty much know that, okay? Now, there are lots of different types of transistors, and we're going to kind of talk about two of them, or sort of two broad categories of them. But this is what they look like, and they have basically three prongs on them, and I'll describe and sort of sketch out what the what these prongs do and how electrically they work. Okay, so these things way less energy, way smaller, and don't burn out like vacuum tubes do. But at first, I mean, these were invented in 1947, basically, and they started to become sort of commercially viable in consumer products in, say, the 50s, mid to late 50s. The first application of them were in radios. Okay, it also allowed for radios to be portable because they were small and you could just use a battery. Okay, good. All right, so let's go over and let me sort of sketch out sort of the idea of how these things work. Okay, so essentially the way that a transistor works, I'm going to kind of draw a really crude sort of sketch of one. Okay, so there are three sort of regions of semiconductor. Okay, and so what is a semiconductor? And what do you guys think? What do you think the word even just means? Yeah. Yeah. Or it sometimes conducts and other times doesn't. Okay. So something that either conducts electricity a little bit, or in our case, what this will mean is that it, depending on certain properties of it, it can either conduct or not conduct. Okay. And that's perfect for our application as a switch, basically. Okay. Now, what kind of material do you think is used for semiconductors? Like what element? I mean, we have the periodic table right there. Yeah, silicon is the number one. Sometimes also germanium. Okay. Um, but yeah, so silicon is really a good one. So if we look at the periodic table, okay, um, well, there it is. Silicon, like carbon, okay, how do you find silicon often in nature? Often not. Yeah, but you can find pretty relatively pure silicon if you just go to a really exotic location. Not so exotic. Go to the beach. What is sand? It's not quartz. It's silicon dioxide. Right? It's just silicon, right? Just piles of it all over the place. Okay, yeah, there's a little bit of oxygen too, right? But that's not too bad, right? Glass, does anybody have a glass bottle in here? Right, is basically crystallized silicon, right, that you heat up and whatnot. So that's really fortunate for us because silicon is a relatively abundant element on the surface of the earth. There's just tons of it, right? As opposed to, you know, something more exotic, like how much uranium is there on the planet? I mean, not a lot, but enough, right? Enough that we can build reactors and bombs and stuff. I mean, maybe we shouldn't build bombs anymore, but um, yeah, we can definitely build reactors. Okay, so silicon is the, you know, kind of the most used element for this. Now, looking at the periodic table where it is, what kind of electrical properties do you think it's going to have? And Jojo, I'm going to be like on you for this because you're the chem major, aren't you? Yeah, okay. So Jojo, what kind of electrical properties do you think silicon might have? given where it is on the periodic table? Yeah, and how is it going to, if it's going to form a pure crystal, like what kind of structure would you expect to see? What kind of bonds would you expect to see? It's honestly going to look a lot like how carbon bonds, right? Which is to say, uh, in a grid structure, sort of a lattice, right? Because how many valence electrons are there on silicon? Six? Six valence electrons on silicon? Mm, you're looking at sulfur, huh? It's way too early. You need some coffee. You're looking at sulfur, not. Yeah, okay. And oxygen, yeah. So four. Thank you. I was like, I know it's early in the morning, but I'm certainly not drunk. All right. So four valence electrons, and how many does it want to have in the valence shell? Eight. Okay. So, which is the same as carbon, by the way, just fewer protons and neutrons. Okay, so it's going to kind of form crystal structures very much like carbon would. This, by the way, in sort of a science fiction kind of way, you could imagine that there could be silicon-based life forms instead of carbon-based life forms because silicon and carbon kind of chemically are relatively similar in some sense. Um, as far as we know there aren't such things, or at least we haven't discovered any on Earth. But perhaps elsewhere in the universe, there's silicon-based life. Who knows? Okay, now what we do with this silicon is deliberately dope it. Okay, so if I just had a hunk of pure silicon crystal, great. But if I deliberately add impurities to it, we call this process doping, then I can change the electrical properties of that part, that material. Okay, and we can dope it in two different ways. Okay, and so when I say dope here, I don't mean like, well, weed, and I don't mean like Lance Armstrong, like with performance enhancing drugs or something. Okay, I just mean deliberately changing the chemical and electrical properties of the material by introducing a little bit of some other chemical or element in this case into what otherwise would just be a hunk of pure silicon. And the ones that are used here are one family either direction of the silicon. Okay, so if I use, for example, phosphorus or nitrogen, then I'm adding a valence electron to the mix, and so I've got some extra electrons in there. And so that piece of it is kind of in doped in the sense that it's got more electrons than it otherwise would have. Okay. On the other hand, if I use something like aluminum or boron, okay, then these, I'm reducing the number of electrons that would otherwise be there. And so in some sense, this is p doped because it's short of electrons, right? Okay, does that kind of make sense? Now, when I say this, like most of it is still silicon, but there's just little bits of boron sprinkled in, or little bits of nitrogen or sulfur, phosphorus sprinkled in. Okay, all right. So I deliberately dope the material in that way. Okay, and in one kind of transistor, the way I do this is to dope it with negative, positive, negative, and I kind of layer them together. Okay, so let me be clear. When I write NP in here, I do not mean nitrogen and phosphorus. I mean negative and positive. Okay, I'm not writing the chemicals. Okay, is that okay? Yeah, okay. Um, and yeah, does it make sense how I'm thinking about the positive ones being deficient of electrons and the negative ones having sort of an extra abundance of them? Yeah. So it's kind of like the good joke. An ion walks into a bar and says to the bartender, "I've lost an electron." And the bartender's like, "Well, are you sure?" And he says, "Well, I'm positive." No, no. Would Dr. Porter be happy with that one? Okay, good. Yeah. Yeah. So, okay, anyway. So this is one way of putting these things together. And this particular kind of transistor, when you do it this way, um, I could also dope it and arrange them in sort of the opposite pattern, PNP, okay? And these two things form a category of what are called BJT transistors, which stands for bipolar junction transistor. Okay. Okay. Good. We know. All right. So let's talk about how one of these things is actually going to work. Let me start with the NPN. So let me go down here a little bit. Okay, so the three prongs that come off of these things, the BJTs, are called the base, the collector, and the emitter. And where they are, the base is the one in the middle always. Okay, but which one's the collector and the emitter depends on which type we're talking about. We'll deal with that later. Okay, so the idea is this. If I apply a small electrical current this way, okay, so small current, then this induces a larger current. Okay, so applying a small amount of current to the base, so there's electricity flowing from the base out the emitter, okay, just a little bit, will induce a much larger amount of current coming through the collector out the emitter. Okay, now this is why these things were originally used as amplifiers, because that's exactly what I've just done here. I am amplifying the signal, the blue signal, to be much more powerful, but the same signal, and that would be the orange one. Okay, so for example, if the blue one was my radio signal, it's going to be turning off and on and off and on and off and on, right? Basically, as the radio waves are hitting the antenna. And then, therefore, the orange current would be turning off and on and off and on, and it's exactly the same pattern, but it's a much stronger signal, and therefore I could connect that to my speakers or whatever and actually hear the radio. Okay, does that make sense? Yeah? Okay, so as an amplifier, that's great, but we can also use this as a switch, because what happens if I don't apply the small current to the base? Nothing. There's no current going through the thing. So I can turn it on and off by just controlling how much current is being applied to the base. And that allows me to have an electrically controlled switch. Okay, does that make sense? Okay, so that's an NPN. The PNPs kind of work in some sense backwards, meaning that, so with the NPN, what happens if I do not apply a current to the base? Is the thing on or off? It's off. There's no current going through it. The PNPs work oppositely. I have to apply current to stop current from flowing. So that would be a switch that's default on, and I have to do something to turn it off. Whereas the NPNs, they're default off, and I have to do something to turn them on. Okay, so that you see how that's kind of mirror image in some sense? Yeah. The PNPs, we tend not to use them that much, but we'll look at some next week when we, like you said, because next week what we're going to do is I've got buckets with circuit breadboards and bags full of all these different parts and wires and stuff, and you guys are going to be, plugging stuff in and getting your hands dirty. Okay, but we just got to get through this theory so we know what the hell we're doing next week. Okay, is that all right? Okay, so now what this means though is there still is actually electricity flowing. Okay, and in particular, you have to actually apply current to the base. Now it's a very small amount. Okay, and we'll talk about how I know how small it is in a moment. Okay, so let me sort of draw a schematic picture of this. Okay, so this entire circuit or piece of a circuit, right? I'm going to draw a symbol for it. Okay, and I know it's not the best drawing ever. This little thing is supposed to be like a little arrowhead. Okay, so it kind of looks like it's the letter K inside a circle, and then there's a little arrow on the bottom leg of the K pointing out. Okay, that's the symbol for an NPN transistor. Okay, so let's sort of talk. Let me add some other pieces in here, and this will make a little bit more sense. Okay, I'm going to need some more paper, so do you guys mind if I scroll here? Okay. Okay, so let me redraw this on another sheet, and I'm going to add a couple things to it. So how could I control, when I say I need to apply a little bit of current, okay, so what are all the symbols here? What's the thing, the K in the circle again? This is our NPN. Anybody happen to know what this symbol is, the one below it that's in a circle? Huh? Oh, okay. The triangle part, yeah, is a delta, but the whole thing is an electrical component. So this is actually the symbol for an LED. Okay, it's a symbol for a diode with two rays of light coming off of it, right? Because a diode is an electrical piece, and a light emitting diode is just one of those that outputs light, right? It's the name. Okay. What about these squiggly lines? Exactly. Okay, those are the symbols for resistors. Now, what is a resistor? What is the point of it? Yeah, it resists the, I mean, the name kind of gives it away, right? It resists electrical current passing through it. And depending, like, it's not as if it just either resists or doesn't. We can actually measure the extent to which it resists. And so, what's the unit for that? Do you happen to remember, Anton? Ohm, right? The ohm is the unit of resistance. 0 ohms would mean no resistance whatsoever. Okay, and the more resistance I use, the less electricity can flow through that thing. Okay, and in this case, if I want to use, like what I would probably use here would be probably a 10K. And the symbol for ohm, by the way, is the capital omega from Greek. And for this, I'd probably only use, say, a 330 ohm resistor. Okay, so I want to apply a very, very, very small amount of current to the base. Okay, so I'm going to put a 10K resistor through there. All right, and what I want to know is how much actual energy am I using? How much electricity is flowing if I have a circuit with a 10K resistor? All right, so does anybody happen to know the fundamental or one of the fundamental equations for this that relates voltage, current, and resistance? No? Uncle Ver? Voltage equals current times resistance. Okay, so what is voltage? What is current and what is resistance? Well, we already talked about resistance. What is current? All right, let me make an analogy here. Or go ahead, Jojo, sorry. So what's current? Yeah, how much is flowing through, okay? And how fast is, in some sense, you could think of that like voltage, okay? Fast is maybe not the right word. Uh, so in French, actually, the word for voltage is puissance or potential, and that's actually a better term for it. So a kind of crude way to think about electrical flow is, what about if I have a garden hose and I got water going through it? Current is how much water is actually going through the garden hose at any moment, okay? And resistance, how would I apply resistance to a garden hose? I could kink it or squeeze it down or something like that, right? And then voltage in the case of the garden hose is kind of like the pressure of the water, right? So how much pressure is there of the water going through your garden hose? Well, what's the sort of faucet pressure in most homes? Does anybody happen to know this? It's more than that. It's more like 60 or so, right? But uh, yeah, 20 psi would be a little low. You better get a plumber out there. Okay, I happen to know these numbers because I was having really weird low water pressure starting mysteriously one day in April. And it turned out that the water company had been doing some work and they had to shut off the water. And so they went into everybody's meter thing and to, crank the shut off valve. But when they opened mine back up, they didn't open it quite all the way. And so I was having all these weird water pressure drops in the house, and I could not figure it out. My plumber couldn't figure it out. And so we finally called the water company, and they're like, everything looks fine. And the technician was like, well, let me just try turning it off and turning it back on. And sure enough, that actually worked. So, yeah, anyway. Okay, so in our case, the voltage that we typically use with electrical circuits, 3.3 or 5 volts, sort of roughly in there. 5 volts for a lot of the stuff that we'll do. And let's take this 10 kilo ohm resistor, and if we pipe it through this equation, well, what I'm trying to do here is I'm solving 5 equals I times 10,000. Oops. And so the current is that, okay? Which is, what's the unit of current, by the way? Yeah, amps, okay. And so what is 5 over 10,000? Well, this would be 0.000 10, 100,000, 10,000. This, yeah, amps. Okay, which is ridiculously low. Yes. Okay. So, and I say that because, well, how much electricity or what amperage would I be able to get out of this wall socket here? Or say most wall sockets at home. What are your sort of regular circuits rated for? Has anybody actually had to do circuit breakers or change an outlet or anything like that? Well, guess what awaits you in 10 years when you guys buy your first house, right? Is a new part of adulting. Um, and yeah, like when I bought my house, my first and well only house, um, within 2 hours of signing all the paperwork, I was already at Home Depot getting stuff, right? So you start your indentured servitude to Home Depot, and the plumber and the electrician and the heating company and the AC people, and then every 20 years you're like, oh, by the way, you need to spend 10 grand on a new roof or whatever. So yeah, adulting sucks, guys. The best way to summarize it is mo money, mo problems. Okay, as I've been told. That's how that goes. Okay, so anyway, the circuits in most home outlets, just, you know, in your regular rooms or stuff, are maybe 15 or 20 amps. 15 is pretty common, right? And that's enough to run sorry, brain just crashed. Refrigerators, crock pots, instant pots, coffee makers, right? Those kinds of things, right? So 15 amps, and that's how much we'd be taking just to turn on the transistor, right? So it's not a whole lot. Now, on the other hand, how much would we be using to actually go through the LED? Well, it'd be 5 over 330, right? Which is a much, much bigger number in comparison, but still pretty dang small in comparison to like an actual light bulb or something, okay? So these things are using very, very, very small amounts of electricity. We can calculate that, and of course, when we build these circuits, we can also measure it. What tools would we need to do that? We've done the math, but how do I know that the math isn't bullshit and I haven't miscalculated or something? If I built this circuit, what would I want to do? What tool would I need? Yeah, I need a multimeter that can measure current and voltage and resistance and all of those sorts of things. Okay. Okay. So one of these by itself, a transistor, a single one by itself, is not all that exciting, right? Because what is this thing going to do? Well, I can control whether or not this LED is on by controlling the current to this wire. If that's all I want to do, why don't I just like get rid of the transistor and control the LED directly, right? This would be inefficient, okay? So I wouldn't actually use a transistor like this in practice. But where this gets interesting is what happens if I start to put several transistors together. Okay. All right. So let me draw a circuit like that, and that will maybe be both where we'll quit today, but also kind of a preview for coming attractions. All right. So let's say that I make the following circuit. Okay. And now I've got two controlling inputs, which I'll label them A and B. And I've got my resistors and I've got my LED just like before. Under what circumstances would that light be on? Yes, Teo. I have to be powering both A and B. Okay? If I power A, then current can get through this transistor. If I power B, it can get through that transistor. But how is it going to get from plus 5 volts to ground? It's got to go through both of them, right? So I have to have both of them being on, and I can only do that if I turn both A and B on, okay? So the light is on precisely when both A and B are on, and it's off otherwise. So what I've just built here is a logic gate, okay? This computes logical AND. Now there are other logic gates, and we'll look at those, okay? For example, there's an OR gate, and with not too much change, I could turn this into one, where it would turn on if one or the other, or even possibly both is turned on, okay? So if I can do logical operations, now we're cooking with gas, okay? Because now we can build computers. Because what is really fundamentally a computer? It's just a fancy pants logic machine, okay? Now, it's going to have thousands of these things instead of just two, right? But that's fundamentally the idea, okay? Is if we can build logic gates, then we can start to think of logic gates as the single unit, and then we can zoom out and start putting lots of logic gates together, and then we can think of those things as units, and then we can zoom out again, and we can start putting these little groups of these things together, and we can zoom out again, and we get to the computers we were taking apart on Wednesday, right? So does that kind of make sense? Yeah. Now, maybe slightly oversimplifying things, but hey, it's CS101, not Physics 499, right? So anyway, okay, so be prepared Monday. I want us to get our hands dirty and actually start building some of these circuits and measuring things electrically. And so next week will be very hands-on and laboratory-y. I'll do a little bit of short streaming at the beginning to kind of get us kicked off, but then most of it will be just, you guys just have to do it. So don't be late or oversleep, or I've already gotten the groveling emails from people like, oh, I'm so sorry I overslept. What am I to do? And it's like, I don't know, fail. So anyway, all right, I will see you guys on Monday. Have a great weekend.